In this segment, we're going to begin by going through some terminology that relates to stereoisomer definitions. Hopefully, this is a review of some of the terminology that we've talked about previously. Then what we're going to do is apply this terminology toward the discussion of alkenes. So let's go ahead and get started with that review of terminology. So the terms that we're going to look at here that we'll be applying later on to example problems are going to be first and foremost the term chiral center. Now, thinking back to chiral centers, remember that was a carbon atom that had 4 different groups bonded to it. And those chiral centers were what we could identify as R or S, depending upon the rankings of the 4 groups that were bonded. And typically we would show a chiral center as a tetrahedral carbon, meaning a carbon with a couple of lines, a wedge, and a dash to make that tetrahedron, showing all those 109.5 degree bond angles around that sp3 carbon. And we would have 4 different groups bonded there, which I'm just going to call A, B, C, and D. And we could assign that configuration of the carbon there as either the R or the S configuration. So a chiral center is the very specific definition of a carbon with 4 different groups bonded to it. So an alkene group will never be a chiral center. Chiral is not a term that applies to carbon-carbon double bonds. So never try to tell me that a carbon-carbon double bond is a chiral center. However, a carbon-carbon double bond does have stereochemistry associated with it, because we talked in the last segment about how we could describe carbon-carbon double bonds potentially as being E or Z configurations. So we do need a terminology that will encompass carbon-carbon double bonds in this concept of stereochemistry. And that term is stereocenter. So stereocenter is a broader term than chiral center, because stereocenter is a term that refers to any location in the molecule where there's stereoisomerism possible. So that is any location in the molecule that we could declare as being RS configuration or as EZ. So stereocenter encompasses both alkene groups that have the possibility of being E or Z, as well as the RS chiral center. So stereocenter is a more general term, a broader term than chiral center, that incorporates both alkenes that could be E or Z, as well as chiral centers. So we'll keep that definition in mind as we roll into some example problems. Another couple of terms that I want to remind you of and make clear what the definitions are for is the term enantiomer. Remember that enantiomer is a non-superimposable mirror image configurational isomer. So that again goes back to that business about chiral centers, that in order for a molecule to have an enantiomer, it has to be a chiral molecule. It has to be a molecule that has 1 or more chiral centers. If there are not 1 or more carbons with 4 different groups bonded to it, then it is not going to have an enantiomer. So it has to have at least 1 chiral carbon or chiral center, a carbon that's 4 different groups bonded to it. So if you have a molecule that has just alkene groups in it and no chiral carbons, that molecule will not have any enantiomers. So to relate enantiomers to one another, what we're always going to be looking for is that within the molecule, every single RS chiral center has changed from R to S or from S to R. In other words, we have created the complete mirror image of the molecule. All the wedges have become dashes, all the dashes have become wedges. On the other hand, all of the EZ stereocenters, all of the configurations of the alkene groups will stay the same. So don't change the configuration of the alkene groups if you're making an enantiomer. If you change the configuration of the alkene group, you're no longer going to have a mirror image. So then on to the next term, which will encompass what happens if we change the configuration of an alkene group, is that we'll get a diastereomer. So diastereomers are defined as pretty much any configurational isomer that is not a mirror image of the other structure that we're comparing it to. So we look at structures that are not mirror images. And to be a diastereomer of another structure, what has to happen is that 1 or more of the RS chiral centers change, but not all of them, because if we change all of them, then we'll end up potentially creating an enantiomer. And the other criteria is that and or some or all of the alkene groups are going to change from E to Z or vice versa. So if we see that every single chiral center has changed, as well as an alkene group changing from E to Z, the two molecules will be related as diastereomers, because if any of the EZ groups change, the two molecules are going to be related to as diastereomers. All right, then onward to the last term that I want to remind you of, and that is the term of the constitutional isomer. So constitutional isomers are going to be two molecules that share the same molecular formula, such as C6H12, but they have different atoms connected to one another. In other words, going from one to another, a branch has moved within the molecule, or the double bond has changed from one spot in the molecule to another, or something along those lines. As a result, the two molecules will have different IUPAC names when we look at the names of the branches or the parent name of the molecule. So that's our constitutional isomer. So we have constitutional isomer, and that's not to be confused with the so-called configurational isomers, which configurational isomers are those enantiomers and diastereomers, the so-called different configurations of the molecule. So what we will do now then, that we've got this definition terminology out of the way, is we're going to go on and look at a couple of example problems that will apply these terms toward looking at molecules. So let's take a look at this example problem. As always, I recommend that you hit pause, try to work through and challenge yourself with this problem, and then we'll go through the answers to see how you did. All right, so going through the solution to this, first off, we're tasked with drawing the structure of Z3-ethyl-2-hexene. So let's go ahead and do that. So this is part A of the problem. So I'm going to go ahead and label it in as A. We need a 6-carbon chain with a carbon-carbon double bond between carbon 2 and carbon 3, since we call this 2-hexene. So I'm going to go to put in my carbon-carbon double bond, and I'm going to specify that that is at carbon 2 to carbon 3 of our 6-carbon chain. I'm going to go ahead then and fill in, relative to carbon number 3 here, the rest of our carbon chain headed to carbon 4, carbon 5, and carbon 6. And they're going from carbon 3 to carbon 4. I put that bond oriented downward. I could have also put it oriented upward. That would have been totally fine as well. What's going to matter is how we orient our groups at carbon number 2 relative to what we have there at carbon 3. We also saw that at carbon number 3, in addition to that parent chain being there, we also see there's an ethyl group at carbon 3. So we need to plug in that ethyl group. So I'll go ahead and do that here at carbon 3. Coming up the other way to finish off our trigonal planar carbon there, we have our ethyl group. So our 3-ethyl is in place. Coming back to carbon number 2, leading away from carbon number 2, we need to go to carbon number 1. So here at carbon number 2, we would have both a hydrogen and a methyl group bonded, that methyl group being part of carbon 1, and we need to decide how to orient that. Do we want to orient the methyl group pointed up like so? Or alternatively, do we want to point it down like this? We have to do so in such a way that will make this the Z configuration. Remember that Z refers to Zusammen, which refers to together. The two groups that are highest ranking need to be on the same face of the molecule. So if we look at our carbon atom on the right there at carbon 3, the higher ranking group of the ethyl group and the propyl group leading away from that stereo center is going to be the 3-carbon chain there, the propyl group that's going on. So therefore, to make the molecule Z, we need for the higher ranking group at carbon 2 to also be on the same face of the molecule, and so therefore we need to orient that group pointed downward so that it is on the same face as that higher ranking group that's bonded at carbon number 3. So I'm going to go ahead and highlight in that higher ranking group is pointed downward. And remember that if we were to assign this as E or Z, we could split the bond down the middle there. We could look at carbon number 3. We'd see that the higher ranking group points downward here. Relative to carbon number 2, the higher rank group points downward as well. And so therefore, this is definitely the Z configuration of the molecule. So that structure that we've just drawn there is our Z3-ethyl-2-hexene. Next up on our list is we are tasked with drawing and naming a diastereomer of A. So this is part B. I'm going to go ahead and first name that diastereomer, because when we're naming diastereomers, what has to change is only the stereochemistry designation. The parent name and the branch names are going to stay exactly as they were. So to get that out of the way, I'm going to write 3-ethyl-2-hexene. And then what we're going to change about the prefix here is going to be just what designates stereochemistry. And so we only had one position that had stereochemistry in this molecule, and that was our Z stereocenter. So we're going to refer to this instead as the E stereocenter in order to make this a diastereomer of what we saw in part A. So we'll go ahead and draw in this. And what this is going to imply is that at one of those two carbon atoms, highlighted in black there, we will have flipped the two groups. So we could either take the methyl group at carbon 2 and instead of pointing it down, point it up, or at carbon number 3, we could take the ethyl group, point that down, and point the propyl group oriented upward. Either way is going to work in doing this. And once we've done it, we need to make sure that we have indeed drawn the E diastereomer. So I'm going to take that methyl group that was going from carbon 2 back to carbon 1 and put that oriented upward instead of downward. Then I'm going to put the double bond in the same as it was all along, leave everything else about the molecule the same, so we still got the 2 carbon chain and our 3 carbon chain. And now that we've drawn this structure, we should be able to deduce that this is indeed the E diastereomer. So what I'm going to do is go ahead as a mental reference there, slice through the bond. I'm going to look at carbon number 3 of the chain. And at carbon number 3 of the chain, that's this carbon right here, our higher ranking group that's bonded to that carbon is the group pointed downwards, so it's our group right here. At carbon number 2, that's the group carbon right here, the higher ranking group is the methyl group. And so now the two higher ranking groups are oriented opposite to one another, one going up, one going down, and therefore we would refer to this molecule as being the E diastereomer. And the E and Z forms of a molecule will always be related to one another as diastereomers. Now onward to part C. And in part C, we are not concerned with what changes with regard to the stereochemistry. What we're concerned about is making a constitutional isomer. So the stereochemistry can be whatever we want in part C here, but we need to change the location of one or more of the atoms within this molecule. And we can do that in a number of different ways. There are a bunch of possible answers here. All of them need to have the same molecular formula that we started with, which was C8H16. And we just need to modify the skeleton in some way. Any correct structure that we draw will have to have at least one ring or pi bond in order to make the index of hydrogen deficiency the same as it was in these other structures, and hence the molecular formula stay the same as it was in the other structures. So we can do a bunch of different possible things here. One of those is that we can go ahead and make our 6 carbon chain again. And I'm going to make the skeleton the same, except I'm going to move the carbon-carbon double bond down here to one end of the molecule. That would certainly yield a constitutional isomer of what we started up top with, because when we move that double bond, we would also have to be moving hydrogen atoms as well. Another possibility is that we could make a 6-atom ring, so a hexagon, and that's 6 atoms, and then put 7, 8 out here like so, and I guarantee you that's going to have your correct molecular formula, because that, like the other structures, have an index of hydrogen deficiency of 1, meaning 1 ring or 1 pi bond. There are other options here as well. To illustrate another possible option, we can make a 5 carbon chain, 1, 2, 3, 4, 5. Then we could plug a double bond in here, plug a branch on here, maybe a branch right here. Let's see if that has the correct number of carbons. Does it have 8 carbons? I think I've only put 7 in at that point, so bring in 1 more. So now at this point, we should have 8 carbon atoms in total. And we do. We have that double bond in there, and I guarantee that's going to have C8H16 as our molecular formula. So these are 3 possible things that you may have come up with as constitutional isomers. Anything that you can count up the numbers of carbons and hydrogens and come up with C8H16, but having a different location of some of the atoms or groups relative to structures A and B up top is going to be a constitutional isomer that would be acceptable. So with that, let's go on to the next example problem. In this problem, we're asked to name all of the possible stereoisomers of 3,4,5-trimethyl-3-heptene. When we're talking about stereoisomers, what we're referring to here are all the possible diastereomers and enantiomers of this molecule, whichever are possible. So we're looking at the sum of diastereomers plus enantiomers. And I will remind you here, going back to our discussion of stereoisomers in full, the 2 to the n rule. The 2 to the n rule, so that if we take 2 to the n, where n is the number of stereocenters, that is the number of locations in the molecule that where EZ or RS are possible, that 2 to the n will give us the total maximum number of stereoisomers that are possible. So we will definitely use that formula here to make sure that we're on track for coming up with the total number of stereoisomers that we need to aim for here. And in order to do that, we need to know how many stereocenters there are in this molecule. The easiest way to deduce how many stereocenters there are in the molecule is to draw it out and look for chiral centers and look for carbon-carbon double bonds where EZ is possible. So let's go ahead and just draw some random stereoisomer of 3,4,5-trimethyl-3-heptene. So we're going to make a 7-carbon chain for our heptene. Make sure we have our 7 carbons in there. I'm going to go ahead and number those just for my own confidence and peace of mind here. Okay, so we have our 7 carbons in place. Since it's called 3-heptene, that means that between carbon 3 and carbon 4, we need to have a carbon-carbon double bond. Bam, we put that in. And at carbon 3, carbon 4, and carbon 5, we need a methyl group. So carbon 3, carbon 4, and carbon 5 all get our methyl groups. Now let's take a look at this molecule and ask ourselves, how many places are there in the molecule where it would be possible to have RS? In other words, how many chiral centers are there? And how many places would it be possible to have E or Z configurations? In other words, how many alkene groups are there where EZ is possible? Okay, so number of chiral centers. Taking a look at this, carbon number 5, definitely a chiral center because it's a carbon that has 4 different groups bonded to it. Then thinking about any other chiral centers, I don't see any, but I do see an EZ location, and that's going to be here between carbon 3 and 4. We have an alkene group, and so we will look at that as a possibility there. So at each of these 2 locations, the possibilities are R or S and E or Z. And so we need to write out all the possible combinations of E, Z, and RS. And to know how many possible combinations there are, we can use the 2 to the n rule. So 2 to the n is going to mean 2 to the 2 because there's 2 places where EZ or RS are possible. So we need to come up with a total of 4 possible stereoisomer names here. Remember that when coming up with names of stereoisomers, all that business about where the branches are located and the parent chain are going to stay the same. So I'm just going to rewrite my 3,4,5-trimethyl-3-heptene to get things rolling here, get us off on the right start. We just got some partial credit there. So we've written in the parent name and the branch names exactly like they were in our structure that we were given. And then we're going to go in here at the front end and we'll plug in our names, or our designations rather, of the stereochemistry. So all the different possible combinations of R, S, and EZ, typically we list the EZ configuration first in one parenthesis and then the RS in a second parenthesis. In this molecule, since we only have one location that's EZ and one location that's RS, we actually don't need to put numbers in here to indicate where the R is and where the E is or whatnot. Instead, we can just plug them in as E or R. It would also be totally fine with me if you put numbers in there as well, but you don't have to here since there is no ambiguity about where the EZ or RS are located based on the structure that we have here. So various combinations. We could do E, R. We could do E, S. We could do Z, R. And we could do Z, S. And those should represent the 4 different possible combinations that we can come up with. The rest of the name for all of these would be the same, so I'm just going to use my ellipsis to indicate that we haven't changed anything about the rest of the names here. And you'll notice that the sum of all of these that we come up with, if we've done this right, should be 4 possible combinations, and indeed it was. So another thing that we can ask when we look at a structure, look at a set of names like this, is we can ask what 2 of those are enantiomers of, if we take any 2 of them, are they enantiomers of one another or are they diastereomers of one another? So for example, taking any 2 of these and taking a look at it, we could take the top one and compare it to, say, the 3rd one on the list here. So we could ask what the relationship is between those 2 compounds that I've listed there in green. And when we ask what the relationship is between those two that I've listed there, rather in red, not green, but red, what we would see is that the ER and ZR, we would describe those as being diastereomers of one another. They're diastereomers because we've changed the configuration of the alkene group. We've left the RS configuration the same. Let's look at another pairing of these to add to our list here. Let's say we took the ES and we compared it to the ZR. So we're always comparing these in pairs. So ES versus ZR, we've changed the configuration at every single location, meaning we've changed E to Z and S to R. These are going to be diastereomers of one another. So they are diastereomers because any time that E changes to Z or vice versa, the two will always be diastereomers. If you see that E has changed to Z or vice versa, automatically get rid of enantiomer as a possibility. We come up with a couple of diastereomers here. What are two that we could pick out that would be enantiomers? Well, enantiomers are going to keep the stereochemistry of the alkene group the same, but change all the R's to S's or S's to R's. So these two structures here that I've bracketed off in green, put the arrows going toward, those are going to be enantiomers of one another because there we left the Z right as it was, but we changed the R to S. Similarly, if we look up top here at the relationship between the ER and the ES, those two we would describe as being related as enantiomers of each other as well, because the E has stayed the same, but all the R's have become S's or the S's have become R's. So those two structures are enantiomers of one another. So in conclusion, by looking at this video and taking all of this in, you should be now comfortable with looking at the relationships between two different molecules that have either alkene groups, chiral carbons, or a combination of both, and using terminology such as diastereomer and enantiomer and things like that to establish the relationship between those compounds.